In another video, I've been talking about this language learning web app, and I'm currently trying to combine it with a Next.js backend template, and that's currently still happening on Codex. But I'm just going to talk a little bit about how the word selection works, because basically the way it works is you have 70 words, or as many as you choose, and so you can see them all listed here. I can click the ones that I know or not, or do a quiz on them. Then there's a series of sentences which are basically generated by OpenAI API calls. Anyway, you get to the end of the 10 sentences, and then you have the option to generate some more. You can either add X number of words, or you can use the same words, or you can reshuffle the whole list with the same number of words. So I'm going to remove 50 words. Now I just have 20. And it's generating the new sentences. And this is just a multiple choice with those new 20 words. But suppose you want to add words. Okay, so say I'm going to add 500 words, or 479 words. And so now there's 499 total. I want to talk about how are those words selected. Or if I go back to the beginning of the menu and I select 200 words, start new game. Then, okay, I get these 200 words. How are these words selected? In the beginning, when I was making this, I actually was doing an API call to generate a list of words in JSON format. But that was very slow because there's a lot of tokens being created, and the output tokens are the slow ones. So if you ask for 200 words, there's really 600 to 1,000 words, because there's the Hindi, English, and the Romanized script with all the brackets and stuff. But then I realized actually generating a list of words is inherently algorithmic. Like you can do it very easily algorithmically. So I went online and I somehow managed to scrape together a list of 3,000 Hindi words, 3,000 common Hindi words. And then I was able to use some ChatGPT gymnastics to make sure that the first 100 are the most common 100, a good approximation of the most common 100, and especially the first 10 and 20 are the probably the most common 10 and 20. So the point is they're ordered by commonness. So the first one is I, you, you again, this, that, what, where. And then if you go further down the list to, say, rank 173, you have Jaldi, quick, 174, Dira, slow, 2099, sweet potato, Shanku, cone, wriggle, boots, gymnasium, less common words. Okay, and it's by no means exhaustive, there's going to be tens of thousands of Hindi words, but for a beginner learner, 3,000 is maybe enough. Now the question is, how do you choose, say, 200 or 500 or 100 words from this list? So you want it to be random to some extent, so every time you generate a new list, it should be different. But we can't just do uniform randomness. You understand? So uniform randomness would be giving each of the 3,000 words the same probability to be selected. That doesn't work, because really you need to make good sentences. You're going to need the first ones, quite a lot of the first ones. By definition, the more common words are going to be more commonly needed. So really there has to be some kind of weighted distribution for the random selection. And I mean, I don't know if there's a rigorous study of this, but it seems highly intuitive that the use of words would follow a power law distribution. It just seems like the kind of thing which would follow a power law. I'm sure somebody has thought more carefully about whether that's true or not, and quite likely determined that it is true. But anyway, that seems like a good sort of first order approximation approach for how to select words. Power law based on commonness. And I'm going to talk a little bit about what exactly that means in just a minute. A small caveat is that the selection of words for valid sentence creation is not going to be independent in the sense that, like, when you have a list of 45 words already chosen, when you choose the 46th, the quality of that selection is going to depend on the previous 45, because it depends how that word is going to interact with the other ones. So really, to make a good selection, you want a non-independent selection criteria, but using an independent power law selection distribution is a good first approximation, probably, and we'll find out by trying it. So anyway, this is just a visualization of the power law distribution, and this is what I used to kind of heuristically choose the parameters for the distribution. So each of these dots, red dots, represents a rank. This is rank 1, rank 2, rank 3. So this rank 1 has been selected, rank 2 has been selected, 3, 4, and so on. And so this is representing a random selection by this power law distribution. It's currently a log y plot. If we make it a regular plot, you can see that on the y-axis is the probability of being selected, essentially. The weighting of that rank to be selected in the probability distribution. Using a log plot just makes it a bit more easy to see, because as you can see with a power law distribution, the smaller ranks are much more likely to be selected than larger ones. But you see that there are also large numbers being selected here, because the power law distribution is what's called a heavy-tailed distribution. So unlike the normal distribution, there is a reasonably high likelihood of extremely divergent selections. Each dot represents a rank, and each rank represents a word. So here we have 1 to 10 unbroken, then there's a gap for 11, 12 to 15 is unbroken, gap for 16, and then here you can see the corresponding words of those ranks in this list. It's the same list. So we have I, you, yeah, this, that, what, where, how, not, so on and so forth. But then we also have rank 2671, which is chacha, whatever that is. And we have fever, shoes, bird, feel, report. Yeah, so you get the idea. And we can change these parameters. So the formula is this WR 1 over R plus B alpha, where alpha is the exponent the exponent parameter. You can see how that changes the distribution. So if alpha is very small, it becomes closer and closer to a uniform distribution, where you see selections are happening across the spectrum. Whereas if alpha is very large, then selections are mostly happening at the beginning, because the probability weighting is so much higher for the small values. And then n is just the number of selections we're making. And then this parameter b isn't standard to a normal a standard power law distribution, but it's kind of like an offset, just to make it so that the very first few ranks in the order aren't so disproportionately more likely to be chosen. So for example, if we make the offset very large and alpha moderate, then you see that the slope is more gentle. Even for high alpha. Okay, so just to give you an idea, this is exactly the selection method that is used. It's the same algorithm used to select the words here. So if I go add 50 more words or 36 more words, you know, the ones the 36 that were selected are exactly selected based on this algorithm, just making sure not to overlap with any previous selections. Yeah, so you get the idea, and the exact parameters used were 5 for b, and then alpha is 1.5. Something like that. and I chose those parameters just by looking at it, honestly. Like I just wanted to make sure that pretty much the first 10 are mostly included, but then you also get some others, and it depends on what n is, because obviously if n is 11, then you're not going to get the first 10. But let's say a standard selection might be about 70 something. So yeah, in that case, you're going to get the first, in this case, 17 without interruption. But then you also get some other ones. So this just creates a nice balance between selecting words which are like functional and create real sentences because they're the common words, whilst also selecting a range of different words that are less common and different words every time, because, you know, we have a set of 3,000 to choose from, and that can always be expanded as well. So, you know, you can really play the game multiple times and get different words each time, and really start to build out your vocabulary. So yeah, that's a summary of how the selection works. I think that's pretty much all I wanted to talk about. You can find this thing to play around with, along with lots of other things, on my ARA.volvox works portfolio page. And you can also make your own ARA.volvox works portfolio page quite easily just by making an account. Just while it's loading, let's see how Codex is doing. Codex, okay, it's on stage 9 of 12, and it's written 6,600 lines of code. Very good. Yeah, so let's see. Where did I put it? Okay, power law word selector. Click on this and then open. It's the same thing. So you can play around with it if you just go to this URL, ARA.volvox/Adam-Aldridge, and then go to JavaScript creations. Or you can play asteroids, which is always fun. And my bragging right is that I made this before AI, the hard way. Okay, let's call it a wrap there.